So we're very excited to have Laurence Perrault-Levasseur kick off the IAIFI Colloquium for the spring semester. I'll briefly introduce Laurence before handing over the mic. So Laurence is an assistant professor at the University of Montreal and an associate member of MILA. She's also a visiting scholar at the Flatiron Institute in New York City. Laurence is a founding member of CIELA, an interdisciplinary research institute associated with University of Montreal, with the mission to contribute to discoveries in astrophysics by developing new machine learning methods. Sounds familiar. All right, so we have Laurence telling us about data-driven strong gravitational lensing. All right, we're back. All right, take it away, Laurence.
I think my mic is on. Yes, that sounds like my mic is on. Well, this is really serial. Okay. Okay, all right. So thanks so much for the introduction. Thanks a lot for the invitation. It's really a pleasure to be here. Before I start, feel free to interrupt me like during the talk, I think, or maybe with the mic situation that doesn't work. But yeah, if you have, you can. I'm very happy to be interrupted and stop me whenever I need to stop talking. Okay. So all right. So like Sid said, I'm going to be talking about some recent research that we've been doing at the intersection of machine learning and strong lensing. So before I get started with the machine learning stuff, I'm going to give a brief introduction to strong lensing. All right. So strong lensing is the formation of multiple images of some distant sources due to the deflection of its light rays by the gravity of some intervening structure. So let's say that here we're on the Earth, and there's two galaxies, one right behind the other one. As the light rays of the background source pass near the foreground galaxy, they get bent, and so they come to us from different angles. And so as a result, here on the Earth, we see multiple images of the same background galaxy. So it's a little bit like looking at the corner of a fish tank. If you've ever noticed, you can see multiple images of the same background fish. So here's Mr. Mango demonstrating this effect. So you can see that as he goes to the corner, maybe I should have put it on the other side, I think. All right, so you can see that when he goes to the corner of the fish tank, you can see two images of the same fish. And let's see, maybe this is going to work better. Okay, so yeah, and it makes an image that's really similar to an actual image of strong lenses that we see in the sky. So here we can see two images of the same background quasar because of the deflection of its light rays by the gravity of the foreground galaxy in orange. Like obviously in this case, the bending of light happens because of gravity rather than like refraction in the glass of the fish tank. Here's another example of a strong lens. So here in this case, we see that the light from the background galaxy wraps around the foreground galaxy and it makes arcs. And those arcs are really a common feature of strong lenses. And the reason for that is the geometry of the lens. So you can actually reproduce an effect similar at home with a wine glass and a candle. So if you look at the flame of a candle through the foot of a wine glass, you can see that it wraps the image of the flame of the candle wraps around the foot of the wine glass, and it makes images that are really similar to actual images of strong lenses that we see like in the sky. And so in this analogy, the flame of the candle is the background galaxy whose image is getting distorted. And the foot of the wine glass is the foreground galaxy that's causing the distortions. So, okay, so this is a really cool astronomical phenomena. But beyond being just a cool party trick and a reason to drink more wine, there's actually a lot of science that we can do with it. So the first thing that we can do is that we can use lensing to study the foot of the wine glass. And the reason for that is that the cause for the distortion is the gravity of the matter inside the foot of the wine glass. So we can basically use it to map out how matter is distributed in the foot of the wine glass. And that's particularly useful for studying the properties of dark matter on sub-galactic scales because it's sensitive to the gravity of the matter regardless of if it emits light or not. And so that's super interesting because right now, well, the contrast is not really great here. Sorry about that. So right now, like on very large scales, on scales larger than galaxies, we have a pretty good handle, we have pretty good constraints on what's the distribution of matter on those scales. But on scales that are smaller than the scales of galaxies, different dark matter models predict very wildly different predictions. So this is like galactic scales here. So on scales smaller than galactic scales, different dark matter models have really wildly different predictions for what should be the clustering of the matter on those scales, so in the foot of the wine glass. And so the goal here would be to be able to map out how matter is distributed in the foot of wine glass to constrain those sub-galactic scales. And so specifically, the way that it works It's a little bit as if we had an extra droplet of water on top of the foot of the wine glass, like here. It's going to cause an additional level of distortion on top of like the general bending of the light coming from the smooth galaxy. And so, for example, here, we can't actually see the droplet of water because it doesn't emit light by itself, but we know that it's there because it's causing this additional level of distortion on top of like the smooth lensing coming from the foot of the wine glass. So it's splitting into two images, and because of that, our brain just infers that there should be something there. So it works exactly the same way with strong lensing. So we want to basically use this to measure how clumpy the foot of the wine glass is, if it's really smooth or if it's really clumpy. And that's related, it's useful because it's related to particle properties of dark matter, like its temperature. So if the temperature of dark matter is really warm, it's going to be much smoother, and it's cold dark matter, it's predicted to be like much more clumpy. All right, so we can also use strong lensing to do other things. Another thing we can use it to do is to study the background source, like the flame of the candle. And that's because lensing magnifies images. So we can use it to study sources that would be otherwise below our sensitivity or resolution limits. So it's really useful to do things like studying the formation of the first galaxies in the history of the universe. And then a third thing we can do, we can use strong lensing for is to do cosmology, for example, by measuring H0. And so I'm going to come back to that in just a little bit. All right. So now that we know all the cool stuff we can do with strong lensing, how do we do it? So let's say I hand you an image of a strong gravitational lens. If you want to infer anything about it, what you need to do is strong lens analysis, which is strong lens modeling, which means that you need to simultaneously be able to infer the undistorted image of the background source, so the flame of the candle, and map out how mass is distributed in the foot of the wine glass. Okay, and so more formally, this is an inverse problem that has this structure like here, where here y is basically, where y is a vector containing the noisy pixels of the lensed image, and here x are the pixels of the background source, and p are the parameters that describe how mass is distributed in the foreground lens, and n is a vector of additive noise. So here, but like we can see, the source parameters, when it's parameterized in this way with like a pixelated flame of the candle, are linear parameters, whereas the parameters that describe how the mass is distributed in the foot of the wine glass are nonlinear parameters. So basically, those parameters enter in a lensing matrix L that then in a way that's nonlinear, and then that gets applied to like the pixels of the background source to lens it in a linear way. So it's basically both a linear and a nonlinear problem. So it's nonlinear in the lens parameters. And because of that, it's a non-convex problem. So it's really hard to sample with traditional methods. Okay. All right. So right now, we know of about a couple hundred strong lensing systems. Well, now with machine learning, we know maybe more, couple thousand. But in the next decade, with LSST and Euclid and the Raman Space Telescope, it's predicted that we're going to discover about 200,000 new strong lensing systems. So it's a really exciting time to be doing strong lensing because we're going to have a lot of constraining power to do all of the cool science we want to be doing with strong lensing. But then the problem is, like I said, it's a non-convex modeling problem. And the likelihood is actually really, really, really poorly behaved. And so it's really hard to sample. So it takes about like 3 days to do the simplest possible like model of a strong lensing system. And so if we scale that to like the data size that we're going to be getting with LSST, it would take 1,400 years to finish the analysis of all of the strong lenses that we're going to find. So this is clearly not scalable. And so this is not going to work. A couple of years ago, we showed that there's actually a really easy solution to this problem. We can just use machine learning. So we can train a very simple CNN to take as an input like the image of the strong lens and then predict the parameters that describe how mass is distributed in the foot of the wine glass. So this is what I'm showing here. So on the y-axis is the prediction from the neural network, and on the x-axis is the ground truth. And then we see that we get like a pretty good way of estimating how mass is distributed. So those nonlinear parameters that describe how mass is distributed in the foot of the wine glass. But then the main point here is that this is 10 million times faster. So instead of taking half an hour, or instead of taking, 1,400 years, it would take half an hour on a laptop. So now like it really becomes possible to tackle this inference problem. Okay, so this was like a while back, many years ago. So since then, we have, on my side, not all, okay, perfect, doesn't matter. Yes, since then we've been working on different aspects of this problem. Like I said, for example, we're also interested in reconstructing the undistorted image of the background source. So like if we observe the lens image, we want to see what's the like the true image of the flame of the candle in the background. And so like I said, this is a linear inverse problem if we parameterize the lens as like a pixelated image. So we could actually invert it analytically. With this, if we like put a prior for but like, okay, so let's say that this is like a 100 by 100 image. This is like a 10,000 dimensional inverse problem. So we need to keep things analytical if we're going to be doing it analytically. And so because it's a really ill-posed inverse problem, we need to have a prior. And so the only prior we can write down if we want to keep things analytical is basically a Gaussian prior. So if we add this prior here, this is the solution we get for the source. And this is the kind of reconstructions that we get. So we can see that it's not really great. There's a lot of noise, so we don't see super well with the contrast, but there's a lot of noise that leaks through the reconstruction. And that comes from this prior here. That's a very simple prior to represent this problem. So what we wanted to do is to know, can we do better with machine learning? So we went about this problem by thinking, could we do this in like a meta-learning kind of way, where we would train a model to learn the optimization process of a class of likelihoods, and to see if we can basically reconstruct the undistorted image of the background source in this way. And so we really like this kind of approach because it's more like a physics-informed machine learning, because it knows about the physical model because we give it the likelihood to optimize, but also it can learn more complex priors coming from training data implicitly, basically. So this is what we got. So here's, again, the mock data. Here's the transcripts we're trying to reconstruct. Here's the reconstruction from the machine learning model, and here's the reconstruction I showed before from linear inversion. So clearly by eye, it's doing a lot better. So we can quantify how much better it's doing by looking at the correlation function. So between like the coherence spectrum between the reconstruction and the ground truth. So in blue is for the RM, and in red is for the linear inversion. And we can see that on all scales, the RM does better than the linear inversion. And so that's really interesting because up to that point, we were mostly thinking of machine learning as a way to speed up the analysis. But that was really the first one we realized, oh, wait, actually, we can get like more accuracy with machine learning than what we could with traditional methods. So, and then the reason for this in this case is that when we're doing the analytical inversion, we're limited to using a very simplistic prior. That's not a really good representation of what our knowledge is galaxies should look like. Like galaxy is much more than a 2-point correlation function. But the machine learning model on the other side is free to learn much more complex prior distribution implicitly from its training data. So that's what allows it to surpass the performance in this way. So from this, we went on to thinking, well, okay, so this is, oh yeah, so we did a bunch of like out of distribution tests. So one of the main criticisms to machine learning is, well, it's super brittle. You trained it and you're in distribution and everything works well, but then what happens if it's out of distribution? So we thought, okay, so we're going to show it like text as the background source, which is definitely not the image of a galaxy. So this is our background source we're trying to reconstruct. And so the lens image of the text is this. So that's the data that the machine learning model is going to see. So it's trying to reconstruct the text at the bottom. Okay, so this is the linear inversion problem, the solution basically. So we see again this problem of the noise leaking, and the resolution is like really non-uniform, and it's not really clear like in the outskirts what's going on. And this is the RM reconstruction. So first of all, I didn't break the model. And the reason why it's so much more robust than like traditional methods is because it knows about the likelihood, so it knows about the physical process that is generating like the data, basically. And then the second thing is that it's actually doing very well, even though it's really out of distribution. Like it has a very uniform distribution, like resolution, and then it doesn't have the noise that leaks through, like is the case for the linear inversion. So that was really encouraging. And then this case is in the case where the lens is super simple. So like the foot of one glass is really smooth, and it can be parameterized by just a handful of simple parameters. But in this case, in reality, real life is a lot more complicated than that. Like, for example, here in the lens, there's like a lot of galaxies that are important, and like it's a lot more messy. So basically what we need is a much more flexible parameterization for the mass distribution in the lens and galaxies. And so what we can do that by using basically a pixelated map that represents like the density in the lens that's been projected down in 2 dimensions. And so we can basically train the same kind of like meta-learning model that learns the process of optimization of the likelihood, but now to reconstruct simultaneously the background source and the foreground lens. And so we can train it like it's similar. So this is the work that my grad student, Alex Adam, has done. So what he's done is he's taken like real images of galaxies for background sources, and he's taken mass maps coming from the LSST and simulation for his lenses, because he needed lenses that were more flexible than just simple parametric model, but still realistic looking galaxies. So this is an example of the kind of reconstructions he got. So the contrast is really not showing, but this is his reconstruction, and this is the ground truth. And so the lens mass is really asymmetrical, and the machine learning model is managing to do a pretty good reconstruction of this. Like, it's not perfect, but it's doing a very good job. And this is something that would be extremely difficult to model with traditional methods. But then we can also look at, this is not going to show really well, but we can look at much more complex mass distributions where there's like a bunch of galaxies together and a lot of subhalos, but we don't really see with our eyes super well because the contrast is really bad. But like, the main point here is that this is a lot more flexible and a lot better than what we would ever be able to do with traditional methods. And here I can't show like a comparison to like a traditional lens modeling method because I cannot model those with traditional methods. They're too complex. I can't compare to traditional methods. This is allowing us to do things that we would not be able to do with traditional methods. So this is super encouraging to be able to extend that to map out how like subhalos are distributed in lensing galaxies. So like specifically the distribution of the matter in the foot of the wine glass. But the problem with everything that I talked about so far is that all these things are just point estimates. And if we want to do science, this is what we want to see. We want to see corner plots with error bars and uncertainties. Okay, so the point is that if machine learning is going to be an essential tool basically for data analysis in upcoming surveys, we need to really think about those models as the statistical model for the data. So it means that we need to have a really good handle on their accuracy and their calibration of those accuracy to make sure that we do accurate scientific inference. So a couple of years ago, we looked into Bayesian neural networks for, I don't understand why is it my laptop sharing that's like so bad with the contrast? That was a bit underwhelming. Okay, yeah, I think it's a Zoom problem. Yeah, I think it's a Zoom thing. It's flicking on the monitor. Yeah, the monitor is just like up and down. Yeah, sorry. Okay, anyway, we're just gonna carry on as if nothing had happened. Okay, so all right, so what Bayesian neural networks are is basically they think of the neural network as just a model of the data, and so instead of having like fixed deterministic weights for the neural network, we replace those by distributions that you learn during training, and then during inference, what you want to do is marginalize over those to get like a distribution of possible parameter values as your output. So this is super promising because it promises to basically incorporate machine learning models in a fully like Bayesian framework. But then the problem is that in practice, they're really hard to train. So in practice, what most people do is that they use variational inference, where they pick a simple parametric distribution that they try to fit to the true like non-parametric distribution that's underlying there. And so they try to learn the values of that parametric distribution during training. So this is an example of where that works well. So here I'm showing like the 1 sigma error bars of like some lensing parameter versus the true value. And here I'm showing the marginal, sorry. Am I the only one hearing the microphone like going crazy? You're not here? Okay, I'm hearing something crazy in my ears right now. Okay, you heard it. Okay. Sorry. It's not just me. I'm not hearing sounds. Okay. All right. Okay, so these are the marginal posteriors that have been sampled with an MCMC in black and the machine learning model in red. And this is for some like real data. This is an ALMA data for this strong lens here that I'm showing. So we see that the two are consistent with each other, which is great. But then the uncertainties from the machine learning model are a little bit wider, and that makes sense because we're taking into account the uncertainty that comes from the machine learning model itself. So that's why it's a bit wider. But for a lot of applications, the precision is not really like the bottleneck of the analysis. For example, if you're interested in background source science, it's just having a lens model that's like really important. So this is still promising for like a lot of applications. So this isn't a case where it works well. It has a lot of pros. It's extremely fast because it's amortized. And what I showed was like interferometric images. So it's actually 1 billion times faster than traditional methods because it's so expensive to analyze interferometric data with strong lensing. So it's really fast, it's amortized. An advantage is that it allows you to marginalize implicitly over nuisance parameters. Like for here, I was interested in the background source, in the foreground lens, sorry, the foot of the wine glass. So I didn't care about the background source, and it was just implicitly marginalizing over it. I didn't have to do anything about it. During training, it learned to do that. And then we can also do like importance sampling if we really care about the precision being like as tight as possible. The caveat is that the variational distribution that we use, there's no guarantee really that it's flexible enough to fit the true underlying distribution that we care about. And so because there's no guarantees like that, there's a lot of problems, and specifically in the high dimension, where it's extremely difficult to get good calibrated uncertainties with like approximate Bayesian neural networks. And so these are some examples where you do like CMB foreground removal, where it's basically impossible to get good calibrated posteriors on this. You always have some bias that you're introducing because of this, the fact that basically your neural network, your variational distribution is not flexible enough. And that's true in general. Like there's no choice of variational. You're never going to have a guarantee that your variational distribution is flexible enough to approximate this. So this is a huge downside for those methods if we really care about accuracy of our posteriors, which we do. So that motivated us to look into simulation-based inference. Okay, so basically the idea here is that you have a neural network that you train with to produce like a compressed statistics that should be informative about your data. And then you try to model the joint distribution of your compressed statistics and your underlying parameter with some density estimator, basically. So this is an example of this for strong lensing parameters. And then this work that's been done by Ronan, our PhD student in Montreal. And so what he's shown, he's compared that with traditional inference and with Bayesian non-IFIs. And what he showed is that basically if you have an accurate simulation pipeline, then you can get things that are as precise and extremely accurate, even when compared to like just traditional, like honest to God MCMCs. So there's another cool thing that you can do with these things is that you can look at hierarchical inference. So like now, instead of being interested into the parameters that describe the distribution of matter in 1 foot of the wine glass, I'm interested in like the distribution over all like possible wine glass that exists. So I can do inference about like those properties of that distribution. But then in practice, I have some selection functions. So I only observe a subset of those wine glasses. And so if I was going to do this inference like this, I would get basically a biased posterior if I didn't correct for that selection function. So what Ronan and Connor have done is that they've shown that they can actually train a neural network to learn that selection function, to model it properly and correct for that bias to get unbiased inference. And the thing that's really cool here is that the selection function is actually a neural network. It's the lens finding neural network that finds lenses. So you can learn the selection function with another neural network and then do the inference with a third neural network. So it's a bunch of neural networks working together in a way that allows you to do unbiased inference, which is sort of pretty cool. Okay, so simulation-based inference has like pros and cons. So the pro is that you can really use the full power of like the machine learning to get your compressed statistics that's as informative as possible about your data. And even if, and then basically you have some statistical guarantees that it's going to converge to your like to a posterior that actually it's not going to be biased. Even if your compressed statistics is biased, you're still not going to bias your inference. You're just going to have less precise inference, so your uncertainties are going to be larger. That's a very important advantage that this has. It's still very fast. Another thing that's good is that if you have like different data and you have different information about their possible parameters, you can, if you're doing an NLE, you can basically you don't have to retrain every time. You can change the prior for different data. So that's another big advantage. And then another thing that's really important is that once you have your posterior, you can get samples that are consistent with your posterior. So if you have a signal in your data, you can investigate where is that signal coming from specifically in my data, which is really important for interpretability. Some of the caveats is that it's hard to marginalize implicitly over nuisance parameters. Typically, you'd have to like explicitly model them, and that makes it like much less tractable for expensive problems where you have large number of nuisance parameters, because you can't really scale this to high dimensional inference. You can limit it to like a couple tens, basically. So that's another downside of this method. All right, so for problems where we have a lot of nuisance parameters, it's much better to look into another kind of method that's called neural ratio estimators. So there's a lot of different flavors of this, but basically they boil down to a classifier that tries to distinguish between two classes. So the two classes of distribution. So the first one is really not showing. I have boxes and stuff here. Okay, so all right. So the first class is basically it's the joint distribution of the parameters and the simulation. So so basically you generate like a set of parameters from your prior, and then you generate some simulations for that. And that's like, this is the first class. It's like the simulation with the parameters that it's related to. The second class is the product of the marginal. So that would be like a simulation with parameter that is or that might or might not be related to that simulation. And so if you train a classifier to distinguish between those two classes, you can actually show that the optimal classifier is going to converge to the ratio between the two distributions. And then because you know the prior, you can use that to recover your posterior. So this is particularly well adapted for low dimensional inference problem where you have a large number of nuisance parameters, because you choose which are the parameters. You can make your simulations as complex as possible, but you choose which ones of the parameters you want to include in the theta. And the ones you don't, that entered in your simulation, they're just going to be implicitly marginalized. Oh, part of my boxes are there. So I didn't do anything, it's just appearing. All right. So one problem that this is really well adapted for is for H0 inference, because we have a really large number of nuisance parameters we want to marginalize over, but we care about one number, H0. And so the way that we can measure H0 with strong lensing is because when we have multiple images, the light that forms those images travels through multiple paths in space-time, and those paths can have different lengths. And so if there's some time variability in the background source, that's going to show up as a time delay between the different images. And then what we can do is we can use those time delays together with like a lens model for the matter in the main lens to infer what the value of H0 is. So, and then we care about H0 because depending on who you talk to, there is or there is not a tension in the value of H0, depending. So from like between the local universe measurements of H0 with supernovae and like early universe measurements of H0 from the CMB, there is a tension that seems to be getting close to 5 sigma. But if you talk to some people, there is a tension, but it's still a good idea to have like another measurement that's independent, that has a different set of systematics to maybe like help inform this debate. So in this case, basically, our parameter is H0, and then our simulations, like the data that we want to feed in the network, are the light curves. So these were light curves that have the information about the time delay and the lens image of the quasar that has information about the lens model. And so in class 1, it's going to be the H0 that corresponds to those simulations. Oh, we almost saw the light curves for 1 second. And then in the other class, it's going to be like some random value of H0 paired with the simulations. So this is work that's been done by my student Ev. So, whoa, this skipped one slide. Okay. So what she's done is that she's like worked with some like very simple sets of simulations where we can actually calculate analytically what the posterior is for the value of H0. And then she's compared that calculation with the value that's output by the NRE. So here there's like the two that are plotted on top of each other. And it's such a good approximation that we can barely see the difference between the two. So then we looked at the calibration of those posteriors, and this is what we got. So the network was a little bit underconfident, but it was not overconfident. So we thought there was a good chance that we could combine the measurement from different lenses to get like a more precise measurement of the value of H0. So that's what she did. And then what she showed is that she can get an unbiased value of H0, even when she combines 3,000 lenses with the NRE. And yeah, and so this is roughly like the number of lenses that we're expecting to get from lens quasar from like LSST. And so the precision that she thinks we could like maybe get is like close to like 1%. So this is really encouraging. Another application of NREs in the area of strong lensing is for doing this inference about like the temperature of dark matter, like the clumpiness, like the parameters that describe how clumpy dark matter should be in lensing galaxies. So this is another example of a problem where we need to marginalize over a very large number of nuisance parameters because we don't care about the actual dark matter map. We just care about the value of the temperature of dark matter. And so this, I feel I've shown like Sid's work here because he's also done work on this, but this is work that's been done on by our postdoc Adam Coogan that show that he can actually infer the value of H0. But this is in the case of like really idealized simulations. So now we have a student that's working on making this a lot more realistic. So tailoring those simulations for LSST to make forecasts about what's the kind of sensitivity we can expect to have just from LSST data alone, which is a question that like nobody has answered. So he's been working on producing those simulations, and then he gets like, when he tests his neural network, he gets like unbiased inference, and he can combine multiple number of lenses, and he can test for the calibration of his posteriors, and he gets like a pretty close to calibrated posterior. So this is really encouraging. But then one question is, how robust are you to out of distribution tests? So what we can do is we can basically train this thing on SIS, so basically galaxies that are completely spherical, and test what happens if we give it galaxy simulations from galaxies that are just a tiny little bit elliptical. So here, like Q equals 1 is an exactly spherical galaxy, and so Q 0.98 is like almost spherical, but just a tiny bit elliptical. And so in this case, it's not really biased. It's good. We're still good to go. But then we make it just a bit less, just a bit more elliptical, and then we start to get biased results. And so this is not super good. As we combine lenses, we start to see that like, indeed it is biased, and we can do a coverage test to see that, yeah, it's all over the place. And so this is a TARP test, actually. So this doesn't mean like underconfident. It could mean like anything. So yes, so this is a bit worrying. And then if we go to Q is equal to 0.9, it's like it just breaks the neural network completely. So we see that it's kind of brittle to out of distribution example, which is not really ideal for the kind of applications that we have in. So, okay, so list of pros and cons for NREs. So we have that NREs are great because they can marginalize over a large number of nuisance parameters implicitly without us needing to worry about it. We just need to include them in our simulations. So it's very powerful to do inference in low dimensional spaces. But the caveat is like we saw from our experiments, it can be very brittle to out of distribution examples in a way that's really hard to predict. And then another caveat, in my opinion, is that they can marginalize over large nuisance parameters. Because once you've done that marginalization, you cannot have access to like posterior samples that are consistent with your data. So let's say that the NRA tells you dark matter temperature is 6 keV. That's it. That's the answer you get, like plus or minus 1, for example. This is all you get to know. Like if you want to know where did that signal come from, is it a small population of like very massive subhalos, or is it a lot of low mass subhalos? Like you have lost the ability of interrogating where did the signal come from in your black box. And so this is a really big downside for machine learning methods, because once we have a result, we're going to want to know where did they come from. We want to interrogate what's going on here. And so I think that if we want to solve this issue, we're really going to have to solve the hard problem, which is the problem of high dimensional inference. And so to solve this problem, there is two main things that are very difficult to do. So first is how to encode very complex priors in high dimensions. And the second one is, if we have a way of encoding those high dimensional priors, how do we sample in really high dimension in a way that is meaningful? Right. The reason why I'm talking about prior is that if we go back to the other example that we had of inference in high dimension, that worked really well with my with my RIM, my meta learning model that was managing to reconstruct pixelated maps. It was working really well because it was managing to learn a more complex prior over like distribution of galaxies or distribution of mass in lensing galaxies. But then the problem with it is that because that prior was learned implicitly, I didn't have the flexibility to sample from it. I was stuck with a point estimate. So what we thought is maybe if we can learn this prior explicitly, then we can sample from it and get uncertainties. So inspired by work from François Lanus, we thought we can learn explicitly this prior distribution. So more specifically, for us, so we want to learn it from samples, and for us, our samples are samples of images of galaxies. So let's say that I have, I'm plotting here in 2D a really high dimensional space. So I have my training data is images of galaxies. So let's say that they're like 100 by 100 images. This is like a 10,000 dimensional space. So all those galaxies, one galaxy is 1 point in a 10 dimensional space. And what I want to do is basically learn this underlying distribution of galaxies to be in a way that I'm able to sample from it, to get new images of galaxies. So one way I can do that is say, well, I'm going to learn the density in that really high dimensional space. So like this. So I know how to do that. What I need to do is I need to maximize the likelihood of the data. But say by optimizing something like the KL divergence. But then the thing that is difficult here is that this is a really non-local problem, because the density at one place is going to need to have global information about the whole space and all the modes in the space, because it needs to be a density, so it needs to be normalized. And because of that normalization factor, it has non-local information about where all the mass of the distribution is in parameter space. And that makes it really, really, really hard to learn for a neural network. And in particular, in high dimension, it's like very difficult to do. But then it turns out that actually, if you want to generate new samples from the underlying distribution of galaxies, the only thing you need to know is the score of the distribution with Langevin sampling. So the score now is the gradient of the log of the distribution. And because it's a gradient, it has only local information about the space. So that makes it, because the gradient of the constant is 0. So basically, because it has only local information, it's much easier for a neural network to learn. So it turns out that we actually can learn these scores with denoising score matching. And so this is work that's been led by my student, Alex. So basically, we can learn the score of this prior distribution with denoising score matching. And then once we have learned it, I don't have time to get into the details, but we can basically sample from it by sampling a realization of Gaussian noise, and then denoising it by solving with Langevin sampling by solving a reverse time SDE to get a brand new image of a galaxy from that distribution that's never been seen before. So these are more examples. So this is work that's been done by my postdoc, Connor Stone. So some of those galaxies are real galaxies, and some of those galaxies are not real galaxies. And I have no idea which one is which. So if you want to go have fun, well, I guess we don't see the link, but there's a link here. And you can go have fun making fake galaxies. It's really addictive. So now we know how to sample from the prior. But we don't want to just sample from the prior. We want to sample from the posterior. So what we need to sample from the posterior is the score of the posterior to sample it from the same way. But I don't know what the score of the posterior is. But I know Bayes' theorem, so I can actually rewrite the score of my posterior as the score of my likelihood plus the score of my prior. So the score of my prior, I'm good. I just learned it. I know what it is. The score of my likelihood is more complicated, but because I am assuming that I have Gaussian noise, and I'm assuming that this is a linear inverse problem because I'm trying to reconstruct the undistorted image of the background source. So these are the linear parameters of my inverse problem. If I'm assuming that I know what my lensing matrix is, I can actually make an approximation that's pretty good to approximate what this likelihood is at high temperature. And so if I do that, this is what I get. So here is my undistorted image of my background source, and this is my my model that I want to recover for that. So here are different mock observations of this with different levels of noise. And here what I'm showing on top is different posterior samples that have been sampled from this. So here we see that when we have really low noise, or really high signal to noise, there's a lot of constraining power in the likelihood. So all of the posterior samples are going to be really close to each other because they're mostly dominated by information coming from the likelihood. So they're going to be really consistent across each other. But as I increase the amount of noise, then it's less and less information in the likelihood, and more information needs to come from the prior to fill up this missing information. And so, but then what's interesting is that in lensing, all the signal usually comes from the highly magnified region in the center of the background galaxy, the way that it's set up here, the lensing problem. And so the center part of the galaxy is always going to be reconstructed really consistently across the different images, because there's a lot of information there in the likelihood. But then the outskirts of the background galaxy, they've been drowned as noise here, so there's not a lot of information. So it needs to draw information from the prior, which is a galaxy prior. So it's going to fill it with some random samples of galaxies coming from the prior distribution. But then if I was going to average over a bunch of those prior samples, there wouldn't be consistent information across the different samples. So I'm not saying that I'm detecting anything significantly beyond the thing that's consistent across the samples, basically. And then in the limit where I have just noise and no signal, I just get a random galaxy sample from my background sources. There's nothing that's reconstructed consistently across the different samples. So it's just, if I was to average the average of my posterior, it'd be nothing. All right, so now I can go and play the same game of out of distribution sampling. So let's say that I have a 7 as my background source. I went to DALL-E. I said, DALL-E, make me a 7 in the shape of a galaxy. Actually, I tried 42, but that didn't work. So, so it turned out to be a 7. So this is my model. And then we can do the same game of looking at like what happens if I have higher and higher, noise levels. So in the case of really high signal to noise, again, I have a lot of information in my likelihood. So I managed to reconstruct the background 7, even though it's really out of distribution for my prior. But then as I increase the level of noise, I need to draw information more and more from my prior because there's less and less information in my likelihood. So it just fills it with galaxy information. So it sort of interpolates between a 7 and a galaxy. And you see the same thing that like the central part of the 7 is the thing that's highly magnified. So it's reconstructed consistently across samples. And then the rest is like filled by galaxy information that's consistent with the part of the 7 that we see. And then in the limit where there's no signal, the information all comes from the prior, so they're just random galaxy samples. Then there's nothing that's consistently reconstructed across different galaxies. So this is interesting. It's also super promising for applying this to real data. But then I said, like before, that we're assuming Gaussian noise here. Oh, no, that's not true. That's not what I'm going to talk about. Sorry, I'm going to talk about that later. Okay, so basically, so I have posterior samples, okay? So, and they look reasonable, like they look like galaxy, that makes sense. Everything seems good, but like how do I actually know that these are samples from the right distribution, like from the posterior that I want to have? So this is like a question of basically accuracy of those samples. Like, do I sample the tails of my distribution appropriately and like with the right like fraction? Okay, so typically the way that this is done is with what is called a coverage test. So basically with a coverage test, you pick an interval and then you want, and then you repeat the experiment multiple times. And then you want the fraction of the time that the true value falls inside that interval to be equal to the volume of probability inside that interval. So you can get like a really nice looking diagonal plot with coverage, probably looking at coverage tests like that. So here, and then typically this is done with the highest density region. So this is what I'm showing here. So this is the highest density region. So it's basically centered around like the peak. So like the 1 sigma region would have 68% of the mass. And so like you'd want the boundary tree to fall 68% of the time in there. So that relies on having access to the density, which is really hard to scale in high dimension. Like if I have images, it's hard to know where's my high density region. And then another thing is that I could be biased and not know. Like for example, if I have a Gaussian like here, and I'm always predicting like to the right of the peak, I'm biased, but I could completely pass this test in a way that's not detectable. But I'm definitely biased. So it's a necessary condition for calibration, but not a sufficient condition for calibration. And so what we've done with my postdoc Pablo is that we've designed a new way of creating those credible like regions in a way that is sort of randomly placed throughout the posterior distribution. And then what we've proven, calculating the coverage probability only relies on having access to a distance in that space, which is really easy to scale in high dimension. It could be like the L1 distance, the L2 distance, but it's something you can calculate in high dimension. And it's also and also what we've done is that we've proved a theorem that shows that this is passing this test is a necessary and sufficient condition for calibration, which means that if you pass this test, you're guaranteed that your posterior is accurate. So we can go, so this, I think, time. All right, maybe we'll skip this. We can ask me how it works more specifically. So like these are a bunch of examples where like underconfident, overconfident, and then this is the case where it's biased, but then the highest density region doesn't capture it. But then with TARP, we can see that it's actually biased and it's not a well-calibrated posterior. So we can look at that for the case of the background source reconstruction, sorry, that I showed. And in the case where we're not careful about this approximation that I talked about for the likelihood, we get biased samples. So this is the orange curve here. But when we make sure that we're careful about the approximation we make in the finite temperature likelihood, then we can manage to get a calibrated posterior, like what I'm showing here. All right, so now we're kind of looks like we're golden. We're ready to apply this to data. And then data looks like this. So data is messy and the noise is not Gaussian. So these are noise samples from the HST, so just patches of skies with nothing in them. So there's a lot of cosmic rays and there's a lot of noise. And this is JWST. So there's also the cosmic rays and there's this like horizontal bands of correlated noise and it's messy and it doesn't look nice. So our Gaussian approximation is definitely going to bias us if we try to just do straight analysis on that. But what we can do is that we can learn the distribution of this noise with a score-based model. We just need to have a bunch of samples of noise, so just empty patches of sky. There's a lot of those, and train a score-based model to sample new realization of noise. So this is what we get. So this is the score-based model that I trained. And I have basically, I can sample from it so I can get new realizations of noise. So one way I can use this is I can use this to do simulation-based inference. So I can use that as my noise simulator that I'm going to add to my simulations to get really good simulations of the data to train my compressed statistics. So that's one way to use this. But you can also use this in an explicit likelihood setting. And so the way that it works is like this. So what I've learned is the score of the noise model with respect to my pixels in my data. But then this noise model is basically equal to my likelihood of my data given my parameters. So these two are just equal. It's actually equal to the likelihood. So I basically just learned the likelihood. So I can learn now this likelihood in an inference setting to sample from it with Langevin sampling. The only thing is that with Langevin sampling, the gradient that comes in here is the gradient of with respect to the parameters of interest. So I actually need to use the chain rule to change variables, and then I end up with like Jacobian of my physical model. But if you're doing machine learning, probably that your physical model is differentiable because it's written in TensorFlow or in Jackson, so you can get the derivative for free. And so in this case, it works like you can actually get this for free, which is like really powerful. And then you can actually use this as, you can use this noise model as your likelihood to analyze your data. This is an example of how this would look like. So this is a real patch of HST noise, but then I've injected the strong lens in it. So I'm trying to reconstruct the parameters of the strong lens, so like the parameter of the foot of the wine glass. And if I assume that my noise is Gaussian and I use a Gaussian likelihood, then I end up with the blue contours here. So clearly, it's, oh, we almost saw it. It's very biased. But then if I use this data-driven likelihood that has the correct noise model, I can manage to get unbiased inference because I'm using the correct like noise model. And so this is very powerful for capturing complex correlated noise in the data, which is what I'm showing here. And then we can do a TARP test to see if we have a calibrated posteriors. And we do, like there's actually, we almost saw the error bar on the TARP part, but yeah, so it is calibrated within the noise of like how you choose how many data points you choose to calibrate to look at the test. All right, so now we have like separately having like, so this was for like an analytic prior. So now I've shown you how to do prior, a data-driven prior and a data-driven likelihood. How about if we put them together to get like the whole thing data-driven? Okay, so this is another example of a linear problem that we can tackle. So this is the problem of PSF deconvolution. So here my prior is going to be galaxy images, and my noise model is going to be data-driven with like this like likelihood that I just showed. So this is the case. This is for HST. So HST, the way that it actually observes is that it's going to do dithering, and then it's going to add them with the drizzle algorithm. So what happens when it dithers is that it shifts the telescope with like by like a sub-pixel amount, and then it's going to use that to have like sub-pixel resolution basically, and then it's going to sort of model that shifting and then like co-add the things, like basically average the things together to get like one final image. But if you look at like the flat fielded data, there's like actually multiple observations of the same like galaxy. It's a galaxy, but individually they don't look great. So we can use that as the data, and then we want to reconstruct what's the underlying true sky emission. So this is the inverse problem. So it's in high dimension because we want to like reconstruct the pixelated image of like the underlying galaxy. The noise, the physical model is just the PSF convolution, and the noise model is a data-driven noise model that comes from empty fields of HST, basically. So if we do that, we can actually do it. This is work that Alex has done, and so this is an example of a posterior sample he gets from this galaxy, like this. So this is actually this, and then you can look at the residuals under his physical model, which includes like the digital algorithm, but not like the co-adding at the end. And these are consistent with just random noise examples. So he manages to model like all the signal out of this. So here's, I don't know how it's going to show, but here's another example. So this is this galaxy that's been one of those observations with HST. And so he can compare how sensitive he is to his specific choice of prior. So he trained one with the prior that comes from like galaxy images, but those have noise because they're observations of like real galaxies. But you can also do the same thing if you have like with illustrious galaxies, if you use some radiative transfer code to like model what the galaxy would look like. So this is the skirt prior here. So these are actually two different priors, and the samples that he gets out of those two different priors. And then there's different sampling schemes that you can have for the reverse time SDE. And so we see that the reconstructions are really consistent across the different choices of prior and the different sampling schemes. So it's robust to like those choices of prior. And another thing that's really interesting is that, like, I don't know if you can see, but there's like those spiral arms that it manages to reconstruct are really not obvious from the data, but they're consistently reconstructed across the different samples. So they're significantly detected. And then we can go to JWST and see what does JWST sees for this galaxy. And that's what it sees. So we see that actually all those features were real. Like we see them when we have high resolution data, which is pretty cool. All right. So okay, and then we can go and do the same game of playing, like, can we reconstruct, like, can we use our prior out of distribution? So this is work that's been done by Noe, who's an undergrad in my group. So specifically what he wanted to do was to reconstruct an image of protoplanetary disks using a galaxy prior, because it kind of has the same shape, for interferometric data. So here the physical model is basically Fourier space transforming and then subsampling the Fourier modes. And the reason that this is difficult is that when you subsample the Fourier mode, you don't have all the information in Fourier space. So if you inverse Fourier transform back to real space, you're going to get an image that looks like that. That doesn't look really good. It's going to have like a lot of side lobes because you have incomplete sampling of Fourier space. So the idea is basically to go from like the Fourier visibilities and for what's the true sky emission. So if you just inverse Fourier transform, you get what's called the dirty image. You can use the clean algorithm to like basically PSF deconvolve this, and this is what you get. But then you can use core-based modeling to get, but with clean, you don't have posterior samples. So you have no idea how good it's going to be. But then you can actually get samples like this. And these are more examples. So it's like, it's robust to like the specific prior and everything. All right, so do I have time to talk about one last thing? Or you can stop me if you want me to stop, it's fine. But this is a paper that came out yesterday. So it's like fresh out of the oven. And so what this is like, okay, so basically we had this TARP test that was great because it worked in high dimension and we could know if we were calibrated or not, but it's a yes or no test. So if we're not calibrated, you never know like how close is close enough to calibration. So it would be really great to have a number to know like how close am I to calibration and what's like acceptable. This is what this paper is. So basically the way that it works is that it calculates the probability that two samples from a generative, two sets of samples come from the same underlying distribution. So the way that this works is that is to realize that if we have like some tessellation of the space, so if we have some region of space, the number of points from one distribution that falls into this like volume follows a binomial distribution. And if I have a full tessellation of my space, like a Voronoi tessellation like here, the number of samples that I have, there should be more samples in other places, but they don't show. Oh, you don't even see them here. Okay, see them on my laptop. There's other samples in the other regions, but they follow a multinomial distribution. And so we can actually, this is super distracting, the fact that it doesn't show. Yeah, so we can basically, oh, we almost saw them. Yeah, so we can define like the expected number of points in each region. And then using that, we can define like statistics like that. That's kind of a chi-square-ish statistic. So we can define this statistics here, which is basically, we can show that this has to follow a binomial distribution. So the point here is that given any sampling distribution or like a generative model, if two sets of sample are generating from the same distribution, then the statistics that I just defined is going to follow a chi-square distribution with like n r minus 1, where nr is the number of regions that I have in my tessellation, degrees of freedom. And so what this allows you to do is basically to test if you're actually like chi-square distributed. So here's an example from like, this is the distribution that's in like 100 dimensions. It's a mixture of Gaussians with like 20 modes. And so we see that like, yes, indeed, it does like follow a chi-square distribution. But it also works for any kind of models. Like for example, if I look at MNIST digits, then they also follow a chi-square distribution under this, like different samples from the same underlying distribution follow a chi-square distribution. So I can use that as a numerical value, and I can turn that in like a p-value that can tell me if what's the probability basically that the two sets of samples come from the same underlying distribution. So you can do it, for example, for the this example of like in 100 dimension of like 20 different modes. If you have a distribution that samples like all the 20 modes, and you have another set of samples that have one mode that's been dropped, you can calculate this distribution as a function of like how many modes. You can calculate this like statistics as a function of how many modes you've dropped. So if you don't drop any mode, you get like this value, but then as you drop more and more modes, it increases. So it means that it's more and more probable that they don't come from the same underlying distribution. So you're very sensitive to not having sampled all the modes of your underlying distribution, even in like 100 dimensions. You can also apply this to MNIST digits to know how well your model is training, how good is your degenerative model as a function of how you train. So initially, so this is an example where we've trained, well, I guess the first VAE we don't see, but we've trained a VAE and a score-based model on MNIST. And we're tracking this statistics as a function of like the number of epochs of training. So when they start out, they're like just basically random noise. So they have a pretty high chi-squared value. But then as they go down, the VAE produces less good sample than the diffusion model. So it's going to saturate like at a high chi-squared. But then as the diffusion model like trains, it gets better and better, and then it gets really close to like the optimal value here. That's like 100 because there's 100 region here. So we know what's like the best like level thing. So we can do that on any kind of, this is MNIST, but you could do it in like high dimensions, and it works for any like time series data, any kind of data. It gives you a number of how close you are to like the underlying distribution. So this is not connected to my computer. This is connected. All right, so I'm going to stop here, because I think I've been talking enough. But I hope that now like that we have all those tests to know if we're calibrated, to know how far we are from our posteriors, and we have all those methods. We're really close to like putting all this together to be able to do exciting science with strong lensing in high dimensions. Thank you.
Thank you very much, Laurence. We have time for a few questions.
Hello, great. Yeah, thank you for the great talk. So I was wondering about the part when you were talking about the calibration tests and the TARP. So you said really quickly that you did something to fix it to make all the samples calibrated, but I didn't quite catch what you did. So could you explain that?
Yeah, so it's the approximation that you do basically comes at the level of the likelihood, because you need to know what's the score of the likelihood at different temperatures to do like denoising diffusion.
Mm-hmm.
And when you at zero temperature, you know what the score of the likelihood is, but at high temperature, you don't know what the score of the likelihood is.
Mm.
And so you can just assume that it's just the same noise level that you should apply, but the noise really lives in the space of the parameters, not in the space of the data. Whereas your likelihood is a function that lives in the space of data, not in the space of the parameters. So you could just say, well, they're the same, and I'm just going to apply the noise. And that's a naive approximation. That's not very good. And that gives you like the biased type thing. But then when you say, no, actually, I'm going to do a better job at it than that, because I know I have a linear model, I can assume that I'm in the regime where my likelihood is informative compared to my prior. And I know I can pass my noise through my physical model and include it in my convolved likelihood, basically. And that's the approximation that you can do. That is not going to work for a nonlinear inverse problem, but in the case of linear inverse problem, when the likelihood is informative compared to the prior, it's a good enough approximation. And then you can quantify like how far you are from the truth. You can actually calculate it. Like you can bound it, basically. Yeah, and so that's when you can get the calibrated.
Great, thank you.
Any more questions?
So I had a question from about 238. It wasn't a slide number. You described your student looking at what you would learn from LSST.
Yeah.
And he generated singular isothermal models.
Yes.
And I'm wondering, there are two components here. First, you generate the training set, and then you train a network on the set. And I'm wondering how the computational resources are required to generate the training set compared to the computational resources to train the network.
So generating the training data for strong lensing is not particularly expensive. It's pretty fast because these are kind of like low resolution images, so there's not that many pixels. If you had like a really high resolution lens image, it would be a different story. Like we had in the work that Alex did. So that was a lot more expensive to get like the illustrious galaxies ray traced through those. That was actually very expensive to generate the training set. But this, because they're analytical profile, it's actually not that expensive. It took him a couple of days to get like a couple 100,000 lenses. So it's not that expensive. And then the training is, again, it's not like very expensive. It's not more than like 1 or 2 days. It's much cheaper to train this than to train like a good score-based model.
So I heard you say a couple of days in 1 day. It sounded like training the network was faster than generating this training.
Yes, yes.
So generating the training set takes more time.
Yes. But it's amortized. So once you've like generated the training data and you've trained, then you're done. You can analyze as many lenses as you want.
All right, I think we're running out of time, so let's thank Laurence again.